All right, guys, in this video, we're going to be starting a brand new unit called gas laws. And we're going to be learning different ways that you can use gases to do work for us. And we use them in a lot of different ways. You may think, okay, well, something as simple as a balloon, we're going to be dealing with things like pressure and volume and temperature. And so what I'm going to do in this video is I'm going to talk us through the different units that are used for pressure, volume, and temperature. Now, when you have something as simple as a balloon, and you air up that balloon, you've changed a couple of different things. By using pressure of air molecules, I've changed the sides of the balloon. It's expanded. So what happens if I take something like that doesn't expand? When you blow into it, like if I took a jar and blow into it, it's not going to go anywhere because it's not an expandable container. But I'm building pressure on the inside of the container. But also the volume, how much space it's taking up. As I add more pressure in there, it gives me more volume. Volume is the space that something takes up. Now, the temperature. The temperature inside here, it's a gas, and this gas is probably going to be about the temperature of my lungs. But the room is not that temperature. So it's about 71 here in the room, but the air coming out of my body is probably going to be closer to 98.7. So there is pressure and volume and temperature changes. So what I want to talk about in this video is what pressure, volume, and temperature are, but at the same time, I'm going to talk about the units that we use in order to do it, all right? So make sure you're taking notes with me. I'm going to show you a couple of demos as well, okay? So let's talk about pressure. Pressure can be done in a lot of different units. If you're talking about the pressure in your tire, as you guys are about to start driving, okay, you have to keep your pressure up. Now, you look on the tire and it tells you how many pounds per square inch that you put into that. But that's not a unit that we use in science. It's not very exact. One of them is called atmospheres. Because our Earth has an atmosphere, there is a layer of air around this rock that we live on called Earth. That air has pressure, and that pressure does work on us, and it pushes on us, okay? And so, as a matter of fact, there's one atmosphere of pressure on the Earth. Okay, and that's the number that goes with that unit. Now, it will be abbreviated 1 ATM. Okay, that's the units they're going to use for pressure. Okay, pressure's pushing on us all the time. Now, you're going to feel it when things like this happen. You get in an airplane, you're going to go flying, you're going to take a flight somewhere. As soon as you start getting off of the ground, your ears start to bother you. You want to chew gum, or you want to try to pop your nose. You're trying to change the pressure. It hurts. It hurts on your eardrum. When you jump underwater, the pressure of the water pushing on your eardrums is painful. So how much pressure is there? Okay, so I'm going to do a little demo here for you a second. I'm going to back this up a little bit, and I have a container right here. Okay, it's got water in it, so you can see it sloshing around. But what I'm also going to do is I have right here is a hot plate that has 2 aluminum cans. Now the aluminum cans, I put just a little bit of water in the bottom of them. Okay, so I'm going to show you there's 2 of them there. Okay, and you can probably see the steam coming off of them. So I've got it boiling. This is a hot plate, and it's getting it really hot, so the water's boiling. Okay, and so what I'm going to do here in a second is I'm going to take this pair of tongs, and I'm going to pick it up, and I'm going to turn this can upside down inside that cold water. Now, I want you to see what happens when you have pressure. All right, so I want you to watch very carefully. Here comes the first one. I'm going to take that can and turn it upside down, and it crushes it, okay? It crushes that can. I want you to notice how much water comes out of there, and it's starting to crush the can. What did that? Change in pressure. The air pressure that's on you and I right now, it tries to smash the can. Now, I have a little bit different level in the other one, so let's watch this other one do this as well. It's been boiling really, really good. Here it comes, ready? And you can hear it smash it, okay? Look how much it smashed that can, and look how much water comes out of there, okay? There's a change in pressure. And when you change pressure, you can get it to do work for you. And so it actually crushed that can. Okay? Now, aluminum's not really, really tough. Okay? But it can actually crush it. Now, why doesn't air pressure crush us? It doesn't crush us because we have bones that are pushing out. Now, if you got home at the end of the day, Mom, I need to lay down. Oh my gosh, air pressure's been so bad. Oh my gosh, then you're sort of a weakling. But we do feel pressure when you have sinus pressure, changes in pressure. We even know the weatherman talks about changes in pressure, low pressure, high pressure. For those of us that have allergies, we can tell when that happens. Okay? And one of those units we measure in science is atmospheres. Now, there's another unit that we also use, so I'm just going to put a bullet here. There's one of them. Another one is this, 101.3 kilopascals. 101.3 kilopascals. Okay? Now, that is just a different unit. So think about temperature. We can have temperature in Celsius and Fahrenheit. These are just two different units. Abbreviated many times, 101.3 kPa. Kilopascal was a scientist. Blaise Pascal was one of the guys that came up with geometry. Very smart guy in science and math. And so the unit was named after him. Thousands of pascals. kPa. Okay? The other one is 760 millimeters of mercury. Okay? 760 millimeters of mercury. In some places in the world, instead of millimeters of mercury, they will use the abbreviation torr. Like in Germany, they will use torr, T-O-R-R. Okay, so let me explain how this one works. Okay, now I'm going to use this water as an example. It wasn't water, but let me use this example. What they found, scientists knew that we had pressure on us all the time, so what they did was they took a really long glass tube. Now, I don't have a glass tube like this, so I'm going to pretend with this ruler. And they had a container with mercury. Now, old thermometers have mercury in it. We've learned it's dangerous, so we don't use mercury like this anymore. But what they did was whenever they stuck that into the mercury and held it still, the mercury would run up the tube. It would always go to the same place. And so they then took a ruler and measured how far it went up there. You want to guess how far it went inside that tube? 760 millimeters. And so they would check the next day. And it would fluctuate a little bit every day. But after they did it many, many, many times, the average pressure of a normal day was 760 millimeters. That's how far it went up that tube. Now, here's what's important for you to know. This and this and this, all three numbers. So I'm going to write it. I can't go low enough on the board, so I'm going to write it right here. 1 atm equals 101.3 kilopascals equals 760 torr or millimeters of mercury. You can call it either one of those. Okay. These three numbers are equal to each other. I'm going to put a star next to this. You need to make sure you write that somewhere where you can use it because you're going to reference it a lot. All three of these numbers are equal to each other. They're just in different units. Okay. And so because they're in different units, sometimes in the lab they're measured in one unit or another, depending on where you are in the world. But there is a conversion. This is the conversion between them. In the next video, I'm going to show you how to use those numbers. But that's where you see them happening. Now I want to show you another demo real quick that deals with pressure. And what I'm going to use this time is a syringe, okay? Just a syringe. And they use this in the physics department. So I borrowed it from them, okay? And what I'm going to use is just an ordinary marshmallow, okay? And I'm going to do it in this big one, and then I'm going to do it in the smaller syringe also. Here's what I'm going to do. Pull this out. If you have one of these at home, this one's really fun, especially if you have younger brothers and sisters, okay? You'll see I put the marshmallow in it. I've had the plunger. The first thing I don't want to do is I don't want to shove the plunger until it smashes the marshmallow, okay? So on the very end of this, I have a... there's no needle there, it's just an opening. So what I'm gonna do is I'm gonna put my thumb over it. And then what I'm gonna do is I'm gonna get that plunger real close. And then what I'm gonna do is I'm gonna have my thumb on there, I'm gonna pull out. And as I do this, I want you to watch that marshmallow starts getting bigger. Now, did you see that? Let's try it again, here it comes. The marshmallow gets bigger as I change pressure. Now you're really gonna see it when I do it like this. So I took the pressure off of it. This time I'm gonna add a ton of pressure on it. So I'm going to keep my thumb right here, hard on it. Now watch, here it comes. The marshmallow gets smaller as I shove that plunger in there. So I'm using pressure to change the size of that marshmallow. Now, you can see it in a big syringe, but you can really see it in a small syringe. Okay, so I just have a smaller one. This would be like a medical syringe that people would use, like maybe you give your puppy dog some medicine sometimes, or small children. This is not a dangerous one. You don't want one that has a needle on it. Okay, it's just open. You would take medicine and you would squirt it into their mouth. Okay, I don't want that wet one I dropped in there. So let's do this one. Now in a small syringe, you can really see what's happening. Okay, so I have it all down at the bottom. I do not want to smash it. First thing I'm going to do is I'm going to make it bigger. Watch this. See that marshmallow get bigger? Let me do it again. It filled up, completely filled up the end of that syringe. Watch as I let it go back. See it change in sizes? Okay, now this time I'm gonna smash it. So I'll have the syringe way down at the end, have my thumb on it. Watch, here it goes. See it getting smaller? And so I can change its size using pressure. So I'm using pressure to do work for me. Now, lots of different things work on this, okay? Not just balloons, okay? There are different apparatuses you can use to use pressure. Pressure can be put on a gas very easily and get it to do work for you. The air conditioner of your home works on this. You take a pressure on a liquid, and as that liquid expands, it gets cold. So all you have to do is turn on a fan and you have air conditioning, okay? You move pressures back and forth from different places, you can get it to do work for you. So those were just a couple of demos. Notice I smashed a can with air pressure, the pressure that's on us right now. How did it smash it? Because there was a change in pressure. When I heated it up and I had boiling water in the bottom, the pressure was really light inside. So when I flipped it upside down, if you didn't catch it, as soon as I turned it upside down in that cold liquid, bang, it smashes it. You can do this on your stove very easily. Take an aluminum can, put a little bit of water in it, okay, just a little bit of water in it, and when you hear it boiling, you just take a pair of tongs, like salad tongs. You don't have to have a pair like this, salad tongs, and turn it over into a pan of cold water. Bang, instantly it smashes it, okay, using air pressure, because the pressure is greater on the outside than the inside, so it smashes it, okay? What happens if you have greater pressure on the inside, okay? If you have greater pressure on the inside, this is what can happen when people will have a soda in a plastic bottle that has a lid on it and they drop it. What sometimes happens is it blows the cap off and it shoots Coke everywhere. Why? The greatest pressure was on the inside. So if the greater pressure is on the inside, that's an explosion. If the greater pressure is on the outside, it's an implosion. So it imploded the can. And then we did one with a syringe and marshmallow. That one's fun, okay? And so pressure, okay? Scuba divers deal with pressure all the time, okay? So when you swim underwater, there's pressure changes that are going on, lots of different things. Astronauts have to deal with pressure. When you go really, really high in an airplane, your pressure changes, okay? Pressure can be measured in atmospheres, kilopascals, or torr, all right? So let's talk next about volume. In all of the gas laws, we're either gonna use milliliters or liters, okay? So that's gonna make it easy because you're used to this. Star, just to make sure you know this, 1 liter is 1,000 milliliters. Okay, you probably already know that, but I'm writing it down just to make sure we have it, okay? And then last but not, so that one's super easy. We're actually pretty familiar with that. Temperature. In the temperature scale, degrees Fahrenheit, degrees Celsius, and then there's this thing called Kelvin that we're gonna deal with here for a second, okay? In science, we don't use Fahrenheit. Fahrenheit is not a very good unit of measurement in science, and the reason it's not is because basically what happens is when they make a thermometer, it's based on a certain substance. For example, you'll know this. Let's go to the one you do know. Celsius, on the Celsius scale, 0 is the freezing point of water, and 100 degrees Celsius is the boiling point of water, because this scale was based on water, okay? And since it was based on water, they have easy numbers for freezing and boiling. What are the numbers of freezing and boiling for Fahrenheit? Well, the freezing point is 32 degrees Celsius. Why such a random number? The boiling point of water is 212 degrees Fahrenheit. What a random number. Why? Because this scale was actually used in a different type of chemistry in what we call organic chemistry. And so it was used for specific labs, but it's not dealing with air temperature and water temperature like these are. That's why we don't use Fahrenheit. So we won't use Fahrenheit in chemistry. We use Celsius. Okay, so based on freezing point of water, now you can go above 100 degrees Celsius, can't you? And you can go below. So you can be -5 degrees Celsius, whatever the case may be. That's pretty easy to do. Now I'm gonna move the camera just a little bit. Okay, and so this one's an easy scale because we have thermometers that are in Celsius or thermometers in Fahrenheit, but again, we're not going to use Fahrenheit. There's a guy that came along that said, okay, I'm going to tell you something that you really need to catch. Watch this very carefully. In the universe, there is heat and there's lack of heat. There is no such thing as cold. The sun makes heat, but the moon doesn't make cold. Cold is the absence of heat. Did you catch that? So if we were to shoot something toward the sun, it gets hotter and hotter and hotter as it gets there. As a matter of fact, it'd probably melt whatever that object is before it ever got to the sun because it's so hot. But in the whole universe, there is heat and there's lack of heat. Okay, we just call lack of heat cold. So when you step outside and it's cold, it's like, well, it's lack of heat. Really, that's what it is. We just give it a name called cold. Same thing with light and dark. Okay, when I turn on a light, there's light. When I turn it off, it is dark. It's really absence of light, but we call it dark. Okay, so light and absence of light, it's the same thing with heat and absence of heat. So I can add heat. Now our sun is about a medium-sized star. Okay, we're the right distance from that for life to occur. On Venus, it's too close. Life cannot live on that planet. Mercury, for sure, it can't. Okay, but there are other stars in the universe that are bigger than ours and they're hotter than ours. Okay, but scientists were looking at, okay, you can add heat, add heat, add heat, add heat, and you can go forever. Keep adding heat. But there should be a point where you take away heat, take away heat, take away heat, take away heat until all heat is gone. Okay, that temperature is what they call absolute zero. Okay, make sure you write that term, absolute zero. Okay, and you're going to put 3 bullets under it. Okay, bullet number 1, it's the coldest temperature in the universe. Coldest temperature in the universe. Bullet number 2, total absence of heat. Total absence of heat. There's no heat. Bullet number 3, all molecules stop. All molecules stop. Now, is it that temperature on Antarctica? No. There's still some heat there. Okay? So what they did in a laboratory, they tried to get as cold as they possibly could get, but could never get to that point. Mathematically, you can take, if you have a graph, for example, when you go, and let's say you had a graph that's measured like this, in your math classes, they will tell you that you can extrapolate or take that graph out forever in both directions. Well, wherever this point is right here, where it would be where there's completely absence of heat. And you can, when you get the slope of that line, you would know what that temperature is. But in a laboratory, we can't even get it to be there. Okay? So they know the temperature of absolute zero. Bullet number 4, add one more bullet. Here it is. Okay? It's way down here. It's negative 273.15 degrees Celsius. That's the coldest temperature in the universe, negative 273.15 degrees Celsius. Where would you find that in the universe? Think about going to Pluto, the planet Pluto, on the back side, the dark side of it, away from the sun, is probably one of the closest places that you would have absolute zero. Okay? And so it's going to be total absence of heat. Okay, so literally molecules would stop. Electrons would stop. All motion would stop. It's crazy what that temperature would be. And again, they've tried it in the laboratory and they just can't get there. Okay? But they know the value and it's been proven over and over and over. This is its value. We just can't reach it. Okay? We just can't reach it. There have been some scientists in the last 10 or 15 years using high pressures and low temperatures have gotten really close, but they haven't gotten to that, the coldest temperature in the universe. Okay? So I'll put this on the scale. This is not drawn to scale at all, but if this is the coldest temperature in the universe, negative 273.15 degrees Celsius, then there's a guy that came along whose name was Kelvin. He actually lived in Britain and he was dubbed a lord. Lord Kelvin came up with what is called the Kelvin scale. And here's what he said. He said, it's logical to me that if this is the coldest temperature in the universe, I'm going to call that 0 on my scale. So everything is adding heat all the way up. So basically, degrees Celsius plus, well, let's do this real quick. If it's a ladder, how many steps did I go down to get there? 273.15, didn't I? So if I'm here, how many steps to get back up to this line? 273.15 degrees Celsius. So here's what he said. If you take degrees Celsius and you add 273.15, you're going to get Kelvin. That's the magic formula. Kelvin numbers are always bigger than Celsius. Did you write that down? Kelvin numbers are always bigger than Celsius. Always. Okay? Where would you use Kelvin in outer space? So if you like astronomy and you look at different parts of different constellations and different stars, all of the temperatures are going to be in Kelvin. It's an absolute scale. Here's what that means. Ready? Because I'll get you on one of these, so be careful. Is there negative Celsius? Can you go below zero? Yes. But on an absolute scale that starts at the lowest temperature in the universe, there is no negative. There are no negative Kelvin numbers. Kelvin is never a negative number, so it's all positive. So do we have thermometers that are Kelvin? I've never seen one. It's a conversion that you use. And there's going to be some of these gas laws that you're going to have to use Kelvin numbers when we deal with temperature. Why? Because if you have negative numbers and you do the math, you give negative things. Imagine if I said, hey, I have -5 dogs at home. Well, that's illogical. You can't have negative objects. Okay? I have -10 Lamborghinis, by the way. Yeah, no, you can't have negative numbers. And so in the mathematics, they had to have a scale that was always positive. And so when we go to do our mathematics, we'll use things in Kelvin. This is actually how we measure it in the lab because we have thermometers in Celsius, but you have to convert it to Kelvin before you can put it into your equation. And you're going to learn how to do those along the way. All of the gas laws are going to deal with pressures. So we saw what pressure looked like, volumes, and temperatures. In the next video, I'm going to teach you how to convert between them.